So the topic of this course is discrete optimization. Maybe I'll just sort of start with a vague definition of like what an optimization problem is. So in the most general possible sense, just take any set X, so let X be a set. And imagine I've got some function f that maps x to the real numbers, right? And a sort of typical problem you see, you want to solve it in, a lot of different math classes, would be like, how do I maximize or minimize this function, right? So our goal in an optimization problem is to find the max or min of f of x over all elements x in capital X, right? In general, though, this is like a hopeless problem, right? You just can't hope to solve this problem in general, right? You could compute f of x for lots of values of x, but there could still be another one. Like if x is infinite size, there could be something else you haven't checked, and that could be the maximum, right? But, I guess a kind of common thing in mathematics is that, a key idea is that if x and f have some kind of structure, like some kind of special properties, then we can sometimes solve this problem, right? So we may be able to solve the problem, let's say. So let's say we may be able to compute the max, for example. Right. And like going all the way back to your days of like calculus, so an example could be, what if x is just a closed interval, 0, 1, and f is, differentiable or something, right? Maybe even twice differentiable or something. F is a really nice function. Well, what do? You find, take the derivative, find the critical points, blah, 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 and then you find the maximum, right? So that's like an example of when you can solve these types of problems. In this course, so another example where you could solve the problem, and this seems even trivial in some sense, is when x is finite, right? So right, because how would you do it? You could just literally compute f of x for every possible value, right, and take the biggest one. So this seems like kind of almost a stupid, example, right? If you have a finite set, but actually that's what this entire course is going to be on. So discrete optimization is about, optimization problems where the set x is finite. But of course, we're not really interested in just solving these problems because, of course, if it's a finite, if you have a finite domain, like I said, you can just check everything and you can solve it. But here's the thing, that's not always practical, right? So, you know, like suppose some company comes to you with some kind of a practical problem. They want to maximize profit or minimize cost, or you know, somehow maximize or minimize something, right? If you just tell them, oh, in theory you can do it, just try everything and find the best solution, yeah, that's not necessarily going to work, because you know it may take, you know, suppose it takes in theory or in practice 100 years to solve that problem with a supercomputer. It's not going to be practical, right? So really the sort of focus of this course is on not just solving problems, but solving them quickly. So maybe I'll just say, yeah, discrete optimization problems are trivial to solve, are trivial to solve, but harder if you want to solve them quickly. So maybe I'll say we want efficient methods to solve them. Okay. So that's really going to be the whole kind of focus of this course. Okay, so yeah, I realize this board seems a bit far away for you guys. I'll write big. Okay, so basically we want some sort of procedures to solve problems. So I need to kind of define things like algorithms, just so we're all on the same page. So an algorithm is, you could be very formal about this, but I'm going to be kind of hand-wavy and just say, so an algorithm is just a list of instructions for solving a problem. Actually, this thing about, you know, when you're maximizing functions in calculus, that's an algorithm, right? You take the derivatives, step one of the algorithm. You take, you know, compute the zeros of the derivative, find the critical points, check the critical points, you know, maybe check the second derivative and things like that to classify them. This is an algorithm, right? This is a list of steps where if you are given a problem, you can just follow the steps and get the solution, right? Get the answer. So basically what we want to do, so for any discrete optimization problem, there is an algorithm. You just check everything. But what we want to do is find algorithms that can be implemented in a small number of steps. What is a step, though? So for the purposes of this course, I'm just going to say an elementary operation in an algorithm so it consists of like one of the following three things. You know, doing an arithmetic operation, like addition, so adding two numbers, subtraction, you know, multiplication, division, whatever. Another key thing we're going to want to be able to do is like compare the size of two numbers. So basically, like adding two numbers, that's going to count as one step of the algorithm. If I take two numbers and I say, if I try to say which one's bigger, that's going to take one step of the algorithm, right? And a third thing is like something called a branching instruction. All I mean by this is like some kind of instruction that says like go back to, so as an example, go back to step 3, right? Like, so there might be you might have an algorithm that has like 5 steps, and you maybe do step 1, step 2, step 3, step 4. Sometimes maybe step 4 sends you back to step 3 to redo it or to do something else. And like, so sometimes you have these loops, and any kind of thing that says like go to this step or something like that, we can call that a branching instruction. Probably you already have some kind of vague feeling of what algorithms are, but I just wanted to make it really kind of clear so we're on the same page. Any questions about any of this? Okay, so let me give you an algorithmic problem, and let's look at an algorithm for it. So yeah, since we're interested in solving problems efficiently, it's going to be important that we can compute the running time of algorithms. So yeah, here's an example. A lot of what I'm saying probably is review from like some computer science class you've taken or something, right? But we will get on to interesting things later. Okay, so suppose you're given n real numbers x1 up to xn. And so this is just a very classic, sorting problem. So what I want you to do is sort the numbers in increasing order and output the result. Okay, so sort the numbers. Right, because these x1 up to xn, they could be anything, right? And we just want to put them in the right order. So maybe let me try to illustrate this issue of efficiency, right? Here's a really, really stupid algorithm. So okay, I'm not going to write the whole algorithm, but I'll sort of explain what. So here's like a really stupid algorithm. So basically, try every possible ordering. And for each ordering, go through every pair I and j with I less than j, and check if the ith number is at most the jth number. Okay, so so can anyone kind of think like, well, okay, it's actually the way I've phrased this, it's maybe hard to tell exactly what the worst case running time for this is, but I mean, how many steps, morally speaking, how many steps is this going to take? Yeah. It may even be more than, but yeah, you're definitely getting an n factorial from here, right? Yeah, I'm actually doing something really silly. I'm going through every pair I and j and checking if they're in the right order. So it's now going to be another n choose 2, yeah. Yeah, the bubble sort would be better, for sure.
And like it's kind of, smarter version of this.
I mean, significantly smarter. Okay, right? Because, yeah, so like if you go through every possible ordering, that's costing, I mean, that's basically taking, there's n factorial possible orderings, and for every single one, I'm checking every pair, which, I mean, that's silly. I could just check consecutive pairs, but I'm even doing worse, right? So yeah, this is like taking the kind of running, so the number of steps, okay, this is an upper bound, but it's going to be, yeah, at most n choose 2 times n factorial. Which I think if like n is something like 60 something, then this number is like bigger than the number of atoms in the universe or something like that, with n being 60, or 65, let's say. So, I mean, there's got to be a better way to order 65 numbers that doesn't take, time corresponding to the number of atoms in the universe. Okay, so right, we want to do things more efficiently. So yeah, there was one suggestion to do something called bubble sort, which is a nice algorithm. I'll do a different one, but it's going to have a similar principle. And I'm not going to give you the best. You can do an algorithm with time n log n, but I'll give you just a sort of simple one. So let's call this. So this is called insertion sort. So, I mean, this is it's kind of a natural thing that I might do if I was actually ordering numbers, right? You start out with an empty list, so I'm just writing, some parentheses here, but this is like a list with nothing in it. And so for each I at least 1, so we want to, in the ith step, we want L, so to be some list y1 up to yi, where like the y1 up to yi are the elements x1 up to xi in the correct order, right? And then if we can do that until I equals n, then we're done, right? But how would you do it? I mean, you start with an empty list. You take x1, just put it in the list, right? Then you take x2, and you look in the list that you have, and you say, okay, should it go before x1 or after x1? And then you put it in. Then you take x3 and you put it in the right position. Take x4, put it in the right position, right? So, so for each for each I, so actually maybe let's put some indices here. I'll call the first list, the initial list L0. I'll call the ith list Li, just to, so we start with Li minus 1. And then find the minimum j such that yj plus 1 is at least as big as xi, and put, insert, which is probably why this is called insertion sort, xi between yj and yj plus 1. And maybe I should say, if there is no such j, then we would just put xi at the end, right? Okay, so this is better. But yeah, in terms of how we're analyzing algorithms, how many elementary operations, I mean, even roughly speaking, are we doing here? And let's not, okay, there might be some kind of maybe there's some branching steps. In some sense, let's just be a little bit rough here, yeah.
N squared.
Yeah, how come?
Because we have two nested, we have a nested for loop, so you have to do all n, and then for each n, you also have to go through all n.
Yeah, totally, yeah. So yeah, the running time, okay, maybe I'll be really, if I was to be really careful about this, I could say on each step, on the ith step, I need to do I minus 1 comparisons, right? Basically, I take my sequence Li minus 1. I've got xi, and I'm trying to figure out where to put it. I have to compare it to that one, to y1, y2. I might have to compare it to everything. So on the ith step, I do I minus 1 comparisons. So yeah, your running time is something like, the sum I equals 1 to n I minus 1, which would just be n minus 1 over 2, which indeed is at most n squared. I told you I was going to try to write big, and now I'm pushing everything into this little corner down here, but yeah. Oh yeah, that's true. Yeah, it's at a weird angle, but yeah, it's bigger. But yeah, are there any questions about this? Okay. So the fact that you're saying n squared is the, basically the answer, that's kind of foreshadowing what we're going to do next, right? I don't really care if this is n times n minus 1 over 2 or whatever. Really we want to know how if you have an algorithm, how does it scale as n grows? Right? If I take some value of n and I double it, is my algorithm going to take 4 times as long? Is it going to take 1,000 times as long? How is this going to scale as the size of n grows? So I'm not so concerned about these constants and things like that. So we should talk about big O notation. There's got to be another eraser somewhere. So yeah, usually we express running time kind of roughly, well, maybe I won't even say that. I'll just say in big O notation. So let me remind you what that is, or tell you for the first time if you're not familiar with it. So let f and g be functions from the naturals to the naturals. So I'm going to give a bunch of notation here. So we write f equals big O of g to mean that there exists a positive constant c such that f of n is at most c times g of n for all n. Right? So I'm going to give you a bunch more of this notation, but just to kind of tie this in to that algorithm, so we could say that algorithm has running time big O n squared, right? So often I'm going to just use big O, like there's not going to be an f and a g, right? I'll just say like this has running time big O n squared, right? So insertion sort has running time big O n squared. And the reason I can say that is because, I mean, we analyzed the running time and we got something like n times n minus 1 over 2. Although I probably skipped some branching instructions and stuff, but that's not a big deal. But anyway, n times n minus 1 over 2 is, well, it's at most 1/2 n squared, right? Because n minus 1 is at most n. Right? So if 1/2 is my capital C, I can say this is big O of n squared, right? Generally speaking, if you've got some kind of like a polynomial, if I've got, n cubed minus 2n squared plus n, plus square root n, right? Really, if you think of how this scales as n grows, right, the dominant term is going to be the n squared, right? Or sorry, the n cubed. Okay. Any questions about anything so far? How comfortable are you guys with big O notation? Okay. Yeah, I think it's a weird notation. It kind of yeah, it takes some getting used to. So yeah. Okay, so I'm going to define more things similar to this. So we write f is equal to omega of g to mean that there exists, so this time I'll write it as a small c, so positive c such that f of n is at least c times g of n for all n. So it's like kind of the same thing as big O, except now we're asking for a lower bound, not an upper bound, right? So f, we write f equals theta of g to mean that well, so the theta is basically going to combine the last two things. So there's two constants. So exists some c, big C and little c. Both of them are positive. Such that basically f of n is sandwiched between little c times g of n and big C times g of n for all n. But I mean, basically, though, this just means like it's the same thing as, you know, f is big O of g and f is so. Right. I guess it's just slightly shorter than writing this and this, right? You just say it's theta of g. Okay, so we also can say f is little o of g. So f is little o g means that like f is like substantially smaller than g. So basically it means that that the limit as n goes to infinity of f of n over g of n is 0. So you should think of this as meaning like g like really dominates f, right? I'm aware that all these definitions are really boring, but I guess it's kind of necessary to kind of set up the language. Okay, so f with a little omega of g. So it's kind of the opposite of little o of g. It's like, it just means that basically f dominates g, right? The ratio goes to infinity. So for example, yeah, n cubed is little omega of n squared, for example. Okay, one more of these. So we write f is 1 plus little o of 1 times g, or sometimes, you know, f with this tilde g. So the idea of this is that basically these have kind of the same order of magnitude up to lower order, like up to small fluctuations. So, so this means that the limit as n goes to infinity of fn over g of n is just 1. Okay. Okay. If at any point I just throw around this notation and you forgot what it means, just ask me though, and then yeah. Oh. Okay, I don't. Oh, maybe they're. Yeah, the thing is, I'm not really going to be able to monitor the chat. It seems like there's three messages in there. So if people are, who are remote, they can feel free to talk in the chat. But if you wanted to talk to me, maybe unmute yourself. But yeah, because I'm not going to be able to run back to the computer all the time. But yeah, are there any questions, including from the Zoom room? Okay. Yeah.
For big O and big omega, is the like for all n more of a, because in the notes it's like for some n not
Yeah, that.
greater at some point.
Yeah, it turns out it doesn't really matter because, I mean, especially because I'm dealing with functions on the natural. So, like, if you imagine, so yeah, I think I may have even updated that like yesterday. But you can also write this as, but you can also but that is a good question. So you could also say f is big O of g means that there's a some c, and there exists some n naught. So I'm just going to write something which turns out to be equivalent. So there exists some n naught such that the inequality we want holds for all n at least n naught. It turns out these are the same thing, though, because suppose that this inequality holds for n bigger than 1,000,000, okay? But now, okay, now look at all the values less than 1,000,000 and compute the worst possible ratio between f of n and g of n for all of those values of n. Worst possible ratio, I mean the biggest, yeah. If I take f of n over g of n, what's the biggest ratio? And I'll just take the maximum of c or that biggest ratio. And that will be, and that will show that you can kind of get rid of the n naught and just say it's for all n. Does that make sense? Yeah. All the finite values you can just take. You can just take the c that works for like n bigger than 1,000,000, or you can, and then take the maximum with all the other ratios, and it'll work, right? Yeah, but that's a good question. So yeah. Any other questions? Okay. What else do I want to say? Okay, maybe we can start actually trying to prove things and stuff. Okay. So the first problem I want to look at is the shortest path problem in digraphs, directed graphs. So I'll define what a directed graph is. So a directed graph or digraph for short is a pair V, comma A where V is a set of vertices and A is a subset of V cross V. So in other words, everything in A is an ordered pair of vertices. Yeah, so it's a set of ordered pairs of vertices called, so the elements of A are called arcs. Or maybe, sometimes maybe you might call them directed edges. Okay, so if you've taken like graph theory or even like second year discrete math, I mean, you might be familiar with these kinds of things, right? So, so it's basically like a graph, except that the arcs, the edges have directions, you know. So, as an example, right, this would be the graph. Sorry, the digraph where the vertices are A, B, C, D. Each of these kind of edges has a direction on it, right? So the direction says like means that in this arc, A is the first vertex, B is the second vertex. So my arcs are like AB, BA, BC, and CD. If I got that right, I don't know. Right, where we, you know, in graph theory, if you have a graph, you usually think of, you know, an arc, an edge UV is the same as VU. But here we just, you know, it's a bit more general. We allow, you know, these to be different things. A, B, and BA are different things. Yeah, so generally for a digraph D, so we're going to say V of D to be the set of vertices and A of D the set of arcs. And if I write like UV is an element of A of D, right, kind of an analogy with graph theory. If I write, so instead of writing the ordered pair parentheses U comma V parentheses, I'll just write UV, right? And that just means there's an arc that points from U to V, right? So and what this really means is that in the digraph, there's an arc like this that exists. You guys seen directed graphs before? Probably most of you have, yeah. Okay. So, yeah, need more notation. Sorry. So a walk in a digraph, I mean, it's just a sequence. I mean, you should think of a directed graph, right? You've got these vertices, you've got these arrows. You can think of them as like one-way streets, right? You can walk from, if there's an arc from U to V, I can take a step from U to V, right? So a walk in a digraph is a sequence V0 up to Vk of vertices such that Vi plus 1 is an arc. So I'll call the digraph D for all indices I. Okay. And then a path is a walk with no repeated vertices. Okay, like so generally in a walk you could just like right? I could start here. I could just walk along this arc, walk, you know. I can come back to the same vertex as much as I want. I could walk around this 100 times and then walk over there. But in a path, you're not allowed to repeat, right? So like this would not be a path, but this is a path, or that's a path, etc. Okay. So here's a classical problem. So the shortest path problem. So suppose someone gives you a digraph. So you're given a digraph D and a length function L, which assigns each arc to a real number. And you're given two vertices S and T. So yeah, you should think of, so this length function basically just assigns a number to every arc that kind of tells you how long it is, right? You could think of that as like a cost, how much it costs to go across that edge or that arc. Maybe there's a toll. Maybe this is some kind of this is some kind of transportation network, and like this road takes some number of hours to drive, and you want to drive from S to T in the shortest amount of time, right? Okay, so the problem find the shortest path from S to T, where the length of a path is just the sum of the lengths of the arcs in the path. So the length of a path, V0 up to Vk, is just the sum, I equals 0 up to k minus 1, of the length of Vi plus 1. Is the problem clear, or any questions about it? Okay. So yeah, just like in any discrete optimization problem, to solve this problem is trivial, right? Just try everything. Just like start at S and just start walking, and just like systematically try every possibility. I mean, and eventually you're going to find the shortest path. You're going to try all the paths, right? Just take the best one. But that's not going to be very practical, and so we want to do this in a better, more intelligent way, right? Okay, so I'm going to show you a famous algorithm called Dijkstra's algorithm. Maybe a show of hands, how many of you have seen Dijkstra's algorithm before? Okay, so it's like kind of like 40% of you. That's not bad. I wanted it to be new, but also kind of familiar, so that's not too bad. Okay, so there's one kind of caveat here in Dijkstra's algorithm. which is that it's only going to work for length functions that are non-negative. So we're going to assume that the length function maps the arcs to non-negative numbers, so the interval 0 up to infinity. Which, like, actually for a lot of practical purposes, that's pretty natural, right? Like if we're talking about actual distances in a network, usually the distances are positive, not negative, right? But actually, kind of interestingly, we're going to see in this course at some point that, like, actually if you allow negative lengths, it actually makes this problem a lot harder, and there is no known polynomial time algorithm for this. So somehow having some restriction on the length function is actually kind of necessary. Okay. So our goal is going to be to output so the length of the shortest path. So I'm going to call this d sub s of v. So s is like the special vertex we had over here, right? Remember, I chose two vertices, and we're looking at paths from s to t. So I'm going to compute this number, ds of v, which is the length of the shortest path from s to v for every vertex v in the digraph. So actually, like the original problem only asked you to find the shortest path from s to t, but actually we're going to find more. We're going to find the shortest path from s to everything. So it's a little bit stronger in some sense. Although, like, in another sense, like, maybe this is natural because, I mean, if there's some vertex in the digraph where I didn't compute the distance from s to that vertex, but I computed it, like, there may be some shorter path to t through that vertex. So, like, maybe I have to compute the distance to every vertex anyway in order to solve the problem. But anyway, this is what we're going to output. But also we're going to output, and a shortest path p sub v from s to t, or sorry, to v. Okay. So that's our goal. We want to compute these numbers, and we actually want to output the actual path, right? Okay, so here's how it's going to go. So at the beginning of the algorithm, we don't know anything yet, right? We haven't analyzed anything. So what I'm going to do is, basically at the beginning, I'm going to say, okay, what is my best guess for ds of v for every vertex? At the beginning, I know nothing. All I know, I know that s is at distance 0 from itself. Because to go from s to s, I just do nothing, right? But everyone else, like, they might be distance infinity. I don't know. So initialize. So, at the very beginning of the algorithm, so I'm trying to come up with, so far, what is my best guess for the length of the shortest path? For s, I know it's 0. Everybody else, I don't know. So I'm going to say at the moment it could be infinity. I have no idea. And then this distance is going to decrease as the algorithm goes on, right? If I reveal some kind of path from s to v that's better than my current shortest path, then I'm going to decrease this value and say, I found a better path, I'm going to decrease it, right? But at the beginning it's infinity, but if I find a path, it's going to go to some non-infinite number, and then it's going to keep going down as the algorithm goes. Okay, and I'm also going to define a function p of v. So, so a small p of v, not big P of v. So this function p of v is going to be equal to s if v is equal to s, and I'm just going to call it null otherwise. And this is also going to be updated during the algorithm. So, okay, the ds function is going to represent the shortest path, the length of the shortest path that I've found so far, starting at s and ending at v. The p of v is going to be like the parent, or the vertex that precedes v on the shortest path that I found so far. So at all points, so this is sort of just a kind of philosophical, kind of comment. So ds of v and p of v are our best guesses so far for the length of the shortest s to v path. So that's this one, and then p of v is the vertex that comes before v on that path. And the reason why it's null at the beginning is, okay, except for s, because the p of s is just going to be s, so it's just like there is nothing that comes before s. But yeah, at the beginning we haven't found any paths that go from s to v, so we're just saying we haven't found any paths, so we don't even know if there is a vertex that comes before v on such a path. A kind of clever thing about this algorithm, right, is that actually if I want to know the shortest path, I don't actually really need to, for every vertex, keep recording the shortest path I found so far. All I really need to know is like who comes before v on that path. Because if I know that, I just go back to that vertex and I say, okay, who comes before that one on the shortest path to that vertex? And then I would just keep going back and recursing until I get to s, right? Any questions about that? I haven't described the algorithm. This is just how you start the algorithm. Okay. Sorry, I need one more thing. I'm going to have a set R, which at the beginning of the algorithm is just the empty set. Okay. R is the set of vertices that I've reached so far in the algorithm, and that's going to keep updating as we go. So at the beginning we haven't done anything, so R is empty. Okay. So here's the kind of main bit of the algorithm. So as long as there's some vertex we haven't reached, so while there exists some vertex v, which is in the digraph, but we haven't reached it yet. We're going to do the following 3 steps. So choose such a v so that the function ds of v is minimum okay. I'm going to add v to the set R, which just means that I'm declaring I've now reached v. I've looked at it. I've done something with it, right? I mean, yeah. Anyway, I'm adding it to R. And now the kind of key step is I want to, for each vertex W, for each vertex W I haven't reached yet. So what I want to do is like kind of say, like for some vertices, remember ds of W, let's say, is my best guess so far for the shortest path to W. If I can find a shorter path that goes through V, I want to exploit that. I want to say, okay, now I've got a shorter path. I'm going to decrease my best guess for the shortest path to that vertex. And I want to then say, then the parent of, the thing that precedes W on the shortest path should be V now, instead of whatever it was before. So for each such vertex, so if there's an arc from V to W, and if I look at my current guess for the distance from S to W, if that's bigger than the distance from S to V plus the length of VW, because I know I can get from S to V in this many steps, right? If I can go from S to V in this many steps and then take one more, or sorry, yeah, if the length of the shortest path is this long from S to V, and then I can take one more step of that length, what I should do is update this. So update ds of W to be ds of V plus the length of VW, and update P of W to be V. Okay. And we just keep doing this until there's nothing left in this set. Any, yeah?
What if you have points that you can't reach? Like if you're trying to go from like in your little example D to A, like there's no way to get there.
That's a good point. Yeah, yeah. I think that's going to be okay. So what would happen, I guess, is at some point. So probably for most, yeah. If you can reach some things and you can't reach other things, in the beginning you're going to keep adding things to R where this number is finite. If there's something you can't reach at all, then there would be no way. Like this number starts at these numbers start at infinity, and they decrease, right? They only decrease when there's some vertex you can reach that can also reach that vertex. Then that's what causes me. Like at some point this will be infinity, and I'm comparing infinity to some finite number, and I decrease it to be a finite number. But the thing is, if you have something you can't reach, the distance function will just stay at infinity forever, because there will be no reason to ever decrease it. It's maybe yeah, I'm not sure if that explanation makes sense. But at some point you would just, I mean, yeah, I guess if this was my S, right? So in the first step, I would add So I start with r equals empty set. Okay, the d function at that vertex is 0, so r would be, I would update it to include this. And then every vertex has, the function's infinity. And then I would just add whatever, it doesn't really matter what I add. Maybe I'd add this one. And then I would check, is it true for all of the things it can reach? Is it true that this inequality holds? Well, it doesn't, because it's infinity, infinity. And I would just never update anything. And it would just say everything's at distance infinity. Yeah. But that's like kind of a, good thing to kind of think about. Any other questions? Okay. Maybe let's analyze the runtime of this, the running time. Actually, maybe I'll get you guys to do it. How does anyone have any sense for how long this is going to take to run? Yeah.
Is it going to be n squared because this is a while loop and then a for loop? So it's nested loop?
Yeah. And that's kind of the same description you gave for the other thing earlier. And I think it's like the outer loop. So yeah, so you've got this outer loop, right, that just keeps checking if this thing is, in each step of the outer loop, I add one thing to R, right? So it's kind of clear that this big loop is going to run n times, because R starts at size 0, then 1, then 2, up to n, right? All the steps in the inside, in principle, even this step could take n steps, because maybe I have to look through all of these vertices to see which one's minimum. Okay, maybe you don't have to do that, I'm not sure. Maybe there's a faster way to do that. But this one, this might take n steps. There might be the number of w's for which VW is an arc. Yeah, that could be n. That could be linear in n. So yeah, you're right, it's going to take big O of n squared steps. So yeah, that's right. So I want to say a theorem. So Dijkstra's algorithm. Well, first of all, I want to say it's correct, meaning it correctly identifies the length of the shortest paths, and has running time so on big O of n squared on digraphs with n vertices. Okay. Okay, so yeah, there's not going to be time to prove that it's correct in this class. I might come back to that next time. But I'll just quickly write down basically what you said about the running time. Right, so the while loop runs for n steps. On each step, or maybe I should say n, rounds or something, or iterations. On each round, so in step 3, you do, let's say, big O of n comparisons. Well, I guess I should be analyzing every possible step. But yeah, this step certainly takes time, big O of n. I could just check this value for every possible v and take the minimum. This takes no time at all. I just put it in the set, and this takes time big O of n. So, yeah, I'll just say basically all steps. Take time big O n per round. And so, yeah, n times n, we've got big O of n squared.